Moving on with systems of linear equations using the matrix method, we already did one three-dimensional example and we checked it by using the graphing calculator. I'm going to go ahead and do another three-dimensional example just so you can see more than one. So in case you want to see how other things work. Okay, I've got my system of equations here. So I'm just going to put this into the augmented matrix, meaning the coefficients or the numbers in front. That's, of course, always the first step if we're ever going to use the matrix method. Make sure I get those numbers right, otherwise I'm definitely not going to get the right answer. And so I have this here. Now, we know that typically the first thing that we want here is a 1 up there. And a lot of times we get 1s by dividing a whole row by something or interchanging two rows. If I were to do that here, that would give me fractions. Now, that's okay, but most people just have a tendency to avoid them, and that's perfectly fine. So I see that the difference between this and the one below it is just 1 unit away. So in this case, to get a 1 up there, I'm going to take row 1, and I'm going to subtract row 2. That's going to be my new row 1. So 3 minus 2 gives me 1. Negative 4 minus a negative 1 is the same thing as negative 4 plus 1, or negative 3. Negative 1 minus 1 is negative 2, and 6 minus a negative 1 is the same thing as 6 plus 1, or 7. My next two rows stay the same. So now I have a 1 there without having to use fractions. Okay? Now, I like to get a 0 below it, or if you can do 2 at once, then go ahead and do that. So I'm going to do that here. First thing is to get rid of the 2. I multiply row 1 by the opposite, or negative 2. Add that to row 2 and replace that in row 2. So scratch work. So 1 times negative 2 is negative 2. Negative 3 times negative 2 is 6. 4, 7 times negative 2 is negative 14. Add those two guys there. So you get 1, negative 3, negative 2, 7 in my first row. That doesn't change. Negative 2 plus 2 gives me 0. 6 minus 1 gives me 5. 4 plus 1 gives me 5. Negative 14 minus 1 gives me negative 15. Now I also want to get rid of this 4. So row 1 times negative 4 plus row 3. Replacing it with row 3. So get rid of this scratch work, don't need it anymore, and I'm going to do new scratch work. So now multiply it by negative 4. So I have negative 4, negative 3 times negative 4 is 12, negative 2 times negative 4 is 8, 7 times negative 4 is negative 28. Add those two rows. So negative 4 plus 4 gives me 0, 12 minus 7 gives me 5, 8 minus 3 gives me 5, and negative 28 plus 13 gives me negative 15. So hopefully at this point you're starting to see, something weird's going on. Okay? If I wanted to follow my next method, that means I would get a 0 where this is. Well, the easiest way to do that is just to take row 2 and subtract row 3. And of course that'll be my new row 3. So row 1 stays the same. Copying down row 2, and now subtracting these. 0 minus 0 gives me 0. 5 minus 5 gives me 0. And then, of course, I get zeros all the way across. So what does that mean if we get a whole row of zeros? Well, if I were to put this back into equation format, that means I would have 0 equals 0, which means we have a true statement. So we can also get these true and false statements in matrix form, just like we could in substitution and elimination form. Now, when we have a true statement, that means that we have the same line. And that means that we need to come up with an answer to give us values for all coordinates x, y, and z of this same line. Okay, so let us figure out what these infinitely many answers are. Well, if we look at our system of equations, if we look at what we have left, We have our first row here. And then we also have this system of equations here. So if we use these two systems of equations, that's going to give us the infinitely many answers that we're going to work with. So let me take my second row, 5y plus 5z is equal to negative 15, and let me solve for one of these variables. And it really doesn't matter which one. Either one's going to be perfectly fine. So I'm just going to solve for my y. So I do that by subtracting 5z from both sides. That gives me 5y is equal to negative 5z minus 15. Of course, then to get y by itself, we divide by 5. And so that tells me that y is equal to negative z minus 3. So that gives me one solution of my answer. Now, since this is in terms of z, we also want to solve for the next variable in terms of the same thing. So I also want to figure out what x is in terms of my z variable. So I'm going to take my first equation that I had up here, which is x minus 3y minus 2z is equal to 7. I'm going to take this y and I'm going to substitute it in for my y there. X minus 3 times negative z minus 3 minus 2z is equal to 7. If I solve this equation for x in terms of z, that gives me my infinitely many solutions. So distribute my negative 3 here. X plus 3z plus 9 minus 2z is equal to 7. So basically I need to take all of this, simplify it, and move it over to the other side. So 3z minus 2z gives me a 1z, so I need to subtract z from both sides. And I also need to subtract this 9 from both sides. So it gives me x is equal to negative z minus 2. So that gives me my x variable. Now I don't have to solve for my z variable because these are in terms of z. So my ordered triple here is my x solution, which is negative z minus 2, my y solution, which is negative z minus 3, and then whatever your z variable represents. So if I wanted to find a specific point on these lines, then we can see, then we just plug in a generic number for z, and that z is going to correspond to both my x and my y variable. Now this is probably a good time to discuss what can actually happen with 3 dimensions. With 2 dimensions, we know that we have 3 possibilities. We have one point of intersection, which is the most common. We can have them be parallel lines, or we can have them be the exact same line. Well, what can it look like when we're talking about 3 dimensions? So let me go ahead and show you an image, just so you can see what's happening here. And so that brings me to this here. So this is the visual representation as to what can happen when we see 3-dimensional system of equations. Now, most of the time we see this first option here where these 3 planes intersect at one point, and so that is our point of intersection. Now, what we saw here in the last time is we saw that there's points of lines in common. So we can see that these 3 dimensions all intersect in such a way that there is one specific line in common. And so that's the answer that we got in the last example. Now, if all those planes are exactly the same, meaning all of the equations are exactly the same, that's what we would get here in example 3. And then in example 4, 5, and 6, the ones on the bottom rows, that would yield us false statements where there is no points in common between all 3 planes. And so this hopefully helps you understand what's actually happening when we see this 3-dimensional figures and what we're trying to solve for. And now you see why your graphing calculator can't graph this, because your graphing calculator can only graph 2 dimensions and not 3 dimensions. Okay, so that moves us on to the last video, which is a word application of solving systems of equations.